In this video, I'm going to show you how to run another simulation, and that is the test case number 8 of the Environment Agency series of benchmarks, which is commonly known as Glasgow flooding. It is a pluvial test case, which also features an inflow from a point source, which is caused by the overflow of a sewage system over the Glasgow urban area. So it has a couple of new features compared to the other test cases, and I'm gonna show you the differences here. The first data is the DEM, which is given in 2-meter resolution with the extension of .dem.raw. So if I open the DEM in QGIS, you'll see that it's a relatively small area with the variation between 21 and 37, which is almost a flat area, and this sewage system overflow is coming from a single point in the vicinity of this area. And of course we have the rainfall over the whole domain, but compared to the previous test case, the rainfall here is spatially uniform but temporally varying. So instead of the .NET CDF file, here we have a file with the extension of .rain, which is a text file with 2 columns. The first column specifies the value of rainfall, and the second column specifies the variation in time, which could be in seconds, hours, or minutes, and here it's based on the minutes. So you can see that the whole simulation and the whole rainfall data is going to be 300 minutes or 5 hours. Another file that we need to set is the .bci file, which specifies the position of the point source inflow, which, as I said before, is mimicking the overflow of a sewage system. So this is the position. We need to identify it to start this line with the character P, and it should be followed by the X and Y position of the point source. And then we need to specify the QVAR keyword, which tells the code that it's going to be a varying discharge input file, and this is the name of the time series of the input file that I'm going to show you now. So the other file that we need to specify is the time series file of the inflow in the point source inflow, and it has an extension of .bdy file. And for those who know how to run lisflood, it's going to be following the same standard as other lisflood time series files. So the first column is the value of the discharge, and the second column is the variation of times starting from 0 all the way down to 300 or 5 hours. In this test case, we also have a specially varying Manning coefficient. So it's not uniform, it's just like the previous test case. And the Manning coefficient file is with the extension of .n, and we can open it using any text file editor, and it shows the variation or the changes of the Manning coefficient. And if I open it in QGIS, it shows that we have a value of 0.02 over the pathways or the roads, and we have a value of 0.05 over all other areas of the domain. The other file that we need to specify is the .stage file, which specifies the positions of the points that we need to record the variations of water depths. And here we have 9 different positions, 9 different staging points, with positions being specified for X and Y direction in the first and second column. So if you remember from the previous video, in order to run the simulation and run the preprocessor for generating the DEM files, I need to copy and paste the executables and the DLL files from the directory of installing lisflood. So I'm going to go to that directory and copy all the executable and DLL files and paste it in the test cases directory. And in order to generate the DEM files for the average and the slope coefficients, which I explained in the previous video, I'm going to open this Windows command line and then type the name of the preprocessor, which is generate dg2dem.exe, and then specify the name of the .par file. So if I press enter, the DEM files of the extension .dem, .dem1x and 1y will be generated. And after that, we can easily run the simulation by putting the name of the executable, lisflood executable, and the name of the .par file. If I press enter, the simulation will start running, and I'll show you after the simulation is finished. So the simulation is finished, showing the whole simulation time of 20 seconds. And we can see that the outputs are saved in a directory named with the same name of the test case. We can see that the 2D files are saved in the .vtk file format, and we have the stage files for the water depths and the velocity. For the VTK files, we can use ParaView to visualize them. So if I open a ParaView and load one of these VTK files, like for example the first one, we can see the generated non-uniform grid. If I change it to representation with edges, so this is the multi-resolution non-uniform grid, which is, as you can see, refined by following the features of the topography. And of course, we can see the results at different saving times. Like, let's load the final 2D file after 5 hours. So this is the water depths after 5 hours. As you can see, it is shown as the variations of the water depth.